Welcome everyone. In this video, we will be looking at Newton's law of gravitation. We will look at how this law is expressed mathematically and then examine some key aspects of its behavior. We will start by looking at the basic effect of gravity, which is that all objects having mass exert an attractive gravitational force on all other objects having mass. This is true for all objects regardless of their size. However, this effect is not at all noticeable for the everyday objects that we interact with. Say, two apples held apart on a table will not suddenly move towards each other the moment we let go. Gravity is only really noticeable when it involves very massive objects like, say, the Earth. Isaac Newton derived a mathematical expression describing the attraction between two objects. He did this at the age of 23. Newton studied at Cambridge until the Plague of London forced the university to close in 1665. Note that, unlike today, online learning was definitely not an option. So Newton returned to his family's home in Woolsthorpe, England, where he developed many of his theories, including the law of gravitation. The popular story is that he saw an apple fall from a tree and questioned why it, or any object for that matter, falls down to the ground rather than sideways or up into the air. The mathematical expression of the law of gravitation is as follows. Considering just two masses, the gravitational force between them is directly proportional to the product of their masses. So the larger the masses, the stronger the force. Now the key thing here is that we assume that the mass of each object is concentrated at their centers. So the force is inversely proportional to the distance measured from the center of mass of each object. Moreover, the force is inversely proportional to the distance squared. So the force decreases dramatically the further apart the objects are placed. The relationship is then multiplied by an empirical physical constant g to yield the magnitude of the gravitational force between the two objects. Force is a vector, and the gravitational force acts in the direction of the line that connects their center of masses. This is indicated by including the symbol r hat, which represents the unit vector pointing along the r-axis. R hat has no value, but communicates that F is now a vector quantity pointing along the r-axis from object 1 to object 2. Thus, the gravitational force on object 1 due to object 2, denoted by F12, is in the direction of the unit vector r along the r-axis. Now, the gravitational force on object 2 due to object 1, denoted by F21, will have the same magnitude as F12, but it will point in the opposite direction. We'll now look at the effect of doubling one of the masses. We start with the original formulation from the previous slide. If we then double the mass of the second object, it will double the original magnitude of the force. So the gravitational force increases by a factor of 2. Now let's see the impact of doubling the distance. We again start with the original formulation. If we double the distance, notice that this change will be squared in the denominator. Thus, the magnitude of the gravitational force decreases by a factor of 4, not 2. So a change in distance results in a larger change in the gravitational force than a change in mass by the same amount. However, Newton was deeply uncomfortable with the notion of action at a distance that his equation implied. He is quoted as saying that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe, no man who has in philosophical matters a competent faculty of thinking could ever fall into it. So yes, he was unhappy with being unable to explain what effectively causes gravity. For that, we need to refer to Einstein's theory of general relativity, but that's a discussion for another day. We will now look at a few key aspects of the law of gravitation. Firstly, the magnitude of the gravitational force acting on mass 1 due to mass 2 is the same as that of mass 2 due to mass 1. Looking at the equations for the two forces, we see that they will yield the same result. However, this does not mean that they will have the same acceleration. F12 equals the mass of the first object times its acceleration toward the second object. Similarly, F21 equals the mass of the second object times its acceleration towards the first object. So let's say the force of gravity between the two objects is 20 units of force. Then if object 1 has 5 units of mass, it will accelerate toward object 2 with 4 units of acceleration. Whereas if the mass of object 2 is twice that of object 1, its acceleration will be half that of object 1. Another key aspect is the following. The gravitational force between two objects is not influenced by the presence or absence of any other object in the universe. With just two objects, the same behavior is seen as before. If we now add a third object, shown as a large gray slab of material, then there is an attractive force between object 1 and object 3, as well as an attractive force between object 2 and object 3. However, these additional forces do not change the force acting between objects 1 and 2. The force between them is still the same, and they still accelerate towards each other at the same rates as they did before, even though they now accelerate toward object 3 as well. This example also demonstrates the principle of superposition, which describes the sum of the forces acting on an object. The net force acting on object 1 is the sum of the force acting on object 1 due to object 2 and the force acting on object 1 due to object 3. Similarly, the net force acting on object 2 is the sum of the force acting on object 2 due to object 1 and the force acting on object 2 due to object 3. Finally, the net force acting on object 3 is the sum of the force acting on object 3 due to object 1 and the force acting on object 3 due to object 2. The last aspect we will look at involves the gravitational constant. The strength of the gravitational force depends on the value of the gravitational constant, which is extremely small at 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. This highlights how weak gravity really is. Hence, an object's mass must be enormous in order to feel its gravity. As an example, the mass of the Earth is 5.98 times 10 to the 24 kilograms, and yet we can still move around its surface rather freely, and even leave its surface with some technical ingenuity. This then concludes the presentation on Newton's law of gravitation. Thank you for your time, and take care.